Hello everyone. This lecture is going to continue to touch upon the topic of inputs and output ports, but for the first topic I want to talk about this lecture, it's going to look a bit of an application of input ports. The specific application of interest is that of interfacing multiple input buttons. Okay, this is from section 4.5 of the course notes. Okay, so if we let me just pull up a figure here. Should be pretty comfortable at this point in the idea of interfacing a switch, like a push button switch, to an input port. In fact, here's an example where we have 4 switches and each switch is connected to a dedicated input port. Okay, but you think about a keypad, like on a keyboard is a perfect example. There are a lot of keys to deal with, and it's quickly going to consume a huge number of inputs if we dedicate an input to every key on a keypad, whether it's a small, just a numeric keypad that's on some phones, phones that have physical buttons, or a full-blown keyboard that we face with as an entry tool for a computer. Okay, so there must be a better way than having, just adding more and more inputs on here as we add more and more buttons. Okay, this is quickly going to consume a lot of input channels, and most likely we're going to run out with your typical microprocessor. Okay, so let's look at another option. And before we do that, just let's remind ourselves of how this specific simple example works here before we expand upon it. Okay, so in this specific example, we have a pull-up resistor for each button, right? As we've talked about before, we have to have a pull-up resistor so that the input isn't floating. So this point on the pull-up resistor and the button is tied directly to an input port for each button. Okay, so when the button is open, as it is shown now, the voltage at this point will be a 1 because we're tied up through that pull-up resistor to whatever our power source here. We can assume 5 volts here for a second. Okay, if we go and we push the button, so let's change this button such that it's closed and shorting out the input, then the voltage at this point, which is at the input of our input port, is going to go to a 0. So button pushed, a 0, button not pushed, a 1 or a high. Okay, I'll also have you note that every button in this row of buttons, right, every one of these buttons shares a common ground, right? They all need a path to ground, right? As we see here, path to ground, and they're all in fact sharing that same connection to ground that we show here over on the left. And in fact, if we were to if we took that ground away, we would no longer be able to detect the press of one of those buttons. When we pressed the button, nothing would happen. The voltage at this point would not change because we would no longer have a connection to 0 volts or ground. Okay? So with that all in mind, let's look at an expanded form of this, of a keypad, or an expanded array of buttons. Okay, so let me bring in this figure. And here we see an array of 16 buttons. We see them all numbered with different values. This is kind of typical of what you might see on a keyboard, like a numeric keypad. In fact, generally we run a lab in our lab environment that makes use of a keypad that has a layout very much like this. What you might notice here is that each row in this system is basically identical to the row of buttons up above, except that there is no permanent ground connection over here that's shared by each row of the buttons. Instead, it's tied to an output port. Okay, and instead of each button being dedicated to a individual input port, we see that there's actually 4 buttons tied to each input port in this example. Okay, so what we have here is some rows. Maybe I'll highlight the buttons. Several rows of buttons and several columns of buttons. Again, here maybe I'll highlight the actual buttons themselves. Okay, so how can we come up with a strategy to determine which of the buttons is pressed if we're only using 4 inputs? Well, we can one by one control the output ports and one at a time pull the output port to 0, again, one and only one, such that now this particular row has a path to ground, and when a button is pressed, it will pull the voltage level at the input. So if this button is pressed, the voltage level now at this point can go to 0, and when we do a read on the input port, this value will read 0. And whichever button is pressed, the same thing. If this button, the next button maybe is left unpressed, this column will stay pulled up to high, so this input will read as a 1. And maybe we leave this button unpressed as well. This column will also be tied up to high, and this will also read as a 1. Maybe this last button, we press it so that this connection now is shorted to 0, and we have a 0 on this input port. What about all the other buttons? What happens if one of these other buttons is pressed? Well, nothing happens, in fact, because if I press one of these other buttons, it has no impact on the state of this line. So let's look at, maybe I'll highlight in a different color here. Let's look at this button. Right? As long as it's unpressed, this line is going to stay high, unless maybe this button up here is pressed. So let's, for a second here, assume that this button at the top is pressed, the whole line is pulled to 0, and pressing or not pressing this button is going to have no effect. Pressing it just ties it to ties the button to 1, but it's actually, because of the diode in here, the connection current will not flow in the reverse direction through that diode. Maybe you're not familiar with diodes, but trust me that current can't flow against the direction of the diode. So even though this entire line is pulled to 0 and this value might seem like it gets pulled to a 1, it can't because of the diode. Okay, so pressing these other buttons will have no effect. So let's think about how this works, a little bit bigger picture here. And maybe I'll pull up another table. Okay, so let's consider this table here. Maybe I'll put it up beside so we can see these both at the same time. Let me slide this over. Let me bring this table up here and talk about how we can scan through these buttons to detect which button is in fact pressed. Okay, so what we're seeing here is this. Let me use yellow again. This these values here are describing what is on these output ports pins, causing each of these rows to take on some state. Okay, and you'll note that only one row at a time is active, if we want to call it that, because we only have a 0 on one row at a time. So we may have in our first checking of the buttons, maybe we'll put a value of 0, 1, 1, 1. We will read the input ports, and if we get a value on the input ports that is shown in the column field here, so these input ports, if we read a value of 0, 1, 1, 1, as is shown here, that means that key 1 must be pressed, right? That means that this button was pressed, and therefore we read a 0, and we know it's only that button because these other rows are not active because they have a 1 on them at this point in time, right? And if the value is 1, 0, 1, 1, well, that is indicating that this button must be pressed, pulling this line now down low, and that's why we're reading a value of 0, 1, 1, 1, and so on, right? So what we end up doing here is we activate our rows one at a time, right? So we activate this row by putting this value on there, and then we can read, and depending on the value we read will determine which of these buttons is pressed. Then at the next scan, the next instant, we put a 0 on this row, and right by writing a value of 1, 0, 1, 1 to this output port, and then we check to see, read the input port, and we check to see which value we read in on the input port, and if it's if the bit E is low, well, this button was pressed. If bit F is low, well, then it's this button is pressed, and so on. Okay, so this is a very common technique of interfacing an array or a matrix of buttons to a computer or to an I/O port while not requiring a huge number of inputs. You see, in this particular case, or inputs and outputs, in this particular case, you see we have 16 buttons, and we needed a total of 8 I/O ports to support those 16 buttons, right? 4 output ports shown on the left here, and 4 input ports shown on the bottom. Right? We could expand this to 25 buttons, and we could have 5 output ports and 5 input ports. Right? So as you scale it up, you see more and more the advantage of the number of buttons you can support with a limited number of I/O. For example, in a much larger case, we could have 8 output ports and 8 input ports for a total of 16 I/O pins, and we could support a 64 button array that's arranged in 8 rows and 8 columns. One thing I'll note is this lookup table that is shown here on the right. It's designed to support just having a single button active at a time when we read the input. So it doesn't account for cases of having multiple button presses. Now you can imagine a more sophisticated algorithm to deal with having multiple button presses, and you can have a look in the course notes about some of the cases of being able to support multiple buttons being pressed, which often occurs in things like a keyboard when people are typing. One other thing I might note is that this may seem like we've opened up an opportunity to miss key presses due to the fact that we have to one by one activate our rows by writing different values on each row as we want to scan each of the rows consecutively. I'll remind you that our computers operate very quickly, and this scanning algorithm can happen extremely fast. In probably nanoseconds or microseconds, we can scan the entire keyboard and then return to start at the top and scan again, right? So just occurred to me I didn't have my good microphone attached, so hopefully from here on out the audio will be a little bit better. Again, just to again stress how quickly we can scan through these arrays. All that's required is putting a 0 just on this row, and then we do a read, right? And then we put a 0 on only the next row, and then we do a read. We put a 0 on the next row, and then we do a read. And then finally we put a 0 on the next row, and then we do a read of the columns. And said that writing 4 outputs consecutively and doing a read in between each one, that can happen extremely quickly, and there is very low likelihood that you're going to miss any key presses. One thing we should also remind ourselves of is that these are physical buttons we're talking about, so we still do have to be concerned with switch bounce, and either use a hardware interface to counteract that switch bounce or come up with a software solution. Thinking about a software solution, I will remind you that might add quite a substantial delay if we have to add a software delay in with every read of our input port. So it's just something to consider if we have a large keyboard array and we want to ensure that we can scan it quickly. Okay, moving on. I want to look at another means of interfacing to memory through an input port that has some additional hardware that may permit a substantial performance enhancement or efficiency in pulling data in from an input port. Okay, this the kind of feature I'm talking about, or the peripheral I'm talking about, is called DMA, which stands for direct memory access. Okay, so before I get into what DMA means, or direct memory access, let's think about how up till now we might read data in from an input port into memory. I want you to realize, maybe it's a good time to mention now, an input port isn't necessarily purely for interfacing to things like buttons and switches. An input port might be an input port for a video card. It might be an input port for serial data. It might be an input port from a hard drive. There's all kinds of things that fall outside of the general description of our computer, and to get that data into the computer, it comes in through an input port. Okay, so let's think about how we pull data in through an input port to memory. Okay, so to read data from an input port, wherever it might be originating from, into memory, and let's talk about how that happens without direct memory access. And really, this is the only way we know of to date, at least based on what we've covered so far in this class. Okay, so without DMA, we would do a read of the input port, and take that value and store it in some register. We would then write the value from the register out to a memory location, okay. So I've simplified the idea quite substantially there, but let's dig in a little bit farther to think about what's involved in those two steps. Okay, so this is a two-step process. And it's inefficient. Okay, so again, let's think a little bit more deeply about what is happening as these reads are happening through our without DMA type example here. Okay, so the processor, maybe I'll just highlight this. The processor is continually involved in this in these steps above. Continually involved, right? Because the processor must initialize a pointer to memory. Right? It has to know where in memory the data is going to be stored. And I'm assuming we're not just storing a single value, we're storing bunch of successive values, right? If it's a single value, who cares? It's not a big deal. This two-step process is fine, but if we're going to be storing multiple data values from that input port into memory, we're going to initialize a pointer to memory such that we can keep incrementing that pointer. Okay, so and further to my point here, initialize a pointer to memory location. We will, as stated above, read the input port. We will, as again stated above, write to memory. We'll have to increment the pointer. So I'm kind of writing this almost in a pseudocode as to the steps that would have to be included in the software to do this. After each write, we'll have to check to see if it's the final address that we want it to transfer. And then we repeat for each word that we want to read in from our input port. Okay, so that two-step process, we now see that there's a bit more involved in simply a read and a write, and more importantly, I want to highlight the fact that the entire way through this sequence of events, the processor is continually involved, right? Initialize the pointer we might do once, but we're going to keep doing this. Read, write to memory, increment pointer, check for final address. Read, right? Write to memory, increment pointer, check for final address. Read, write, increment pointer, check for final address. So with every word, that's going to happen. Okay, now let's look at what DMA offers us as an alternative. DMA standing for, again, direct memory access. Okay, with DMA, when a DMA transfer is initiated, the processor is halted and isolated from the system buses, the external system buses. I'll show a diagram here in a second that hopefully will make this clear. This is done through the control unit whose bus connections are put into a high impedance state. Okay. Next, our DMA control unit, so the input port itself will have its own DMA control unit that allows this direct memory access. Okay, so I'll say this DMA control unit, which is within the I/O port, between the port and system buses. Okay, so that's just a description of where that DMA control unit exists within the I/O port itself. The DMA control unit is going to connect to the bus and it will take control of generating the appropriate bus signals to store a number of words from the input port directly to consecutive memory locations. Okay, so no, the processor doesn't need to be involved. It's a one-step process because the data comes in and from the input port goes directly to memory as controlled by the control unit. You don't have to read into a register then write that register out. So it can be extremely fast. In terms of the process of how the DMA knows what to do, we have to provide the DMA transfer with some information, and the processor will set up that DMA transfer before it's initiated. So the DMA transfer requires that the processor provides the destination memory address of the first word to be stored, and the number of words to be stored. Okay, so with that information, once the DMA transfer is initiated, again, DMA control unit connects to the bus, generates the bus signal to store a number of words. The number of words was specified when it started, and where those words go is specified when the destination of that first word was specified. So we say, I want you to store 1,024 words beginning at address 10000 in hex, and go, and the DMA control unit will take over. So we have a look at what our computer system might look like with this DMA control unit in place. Here's an image showing that DMA control unit that sits between my input port and my system buses, and it then has the ability to make direct connection to the memory and address that memory directly while the system bus is disconnected from the processor. Now, we said the processor is halted, but some processors may have the ability to still do internal operations that don't require access to this external system bus. We may also have the case where the DMA control unit has an alternate path to memory. So we talked about some of the different types of memory. Maybe this memory is a dual port memory that has a second path for accessing the memory and writing to that memory. So we don't need these connections to the system bus. So they can stay connected. Everything else can go on as normal, and the DMA can write data directly into memory through this secondary path. Okay, so if you have a look at some different hardware, different micro controllers, hard drives, there's many different applications that you use DMA to accelerate the transfer of data from an input port and to offload some of the work that's required by the processor and to free it up to do other things.